In this section, we're going to look at how we can write electron configurations using the information that we've already learned about energy levels and orbital types. When we refer to electron configurations, we're talking about how electrons order and arrange themselves around the nucleus of an atom. There are three fundamental rules you need to keep in mind whenever you're writing an electron configuration. The first rule is that a maximum of 2 electrons can occupy any single individual orbital. Doesn't matter what type of orbital it is, an s orbital, a p orbital, a d orbital, or an f orbital. A maximum of 2 electrons can occupy any single individual orbital. Second rule is that electrons will occupy lowest energy orbitals available first before filling the next highest energy orbital available. So energy of orbitals has to do with their size, as we discussed. Electrons want to be in orbitals that are closest to the nucleus, smallest in size, low energy, great stability. So electrons will always occupy the lowest energy orbital available to them first before filling the next highest energy orbital. The third and last rule is, I'm going to state it, but it's a little difficult to explain here. You're just going to have to be patient until we discuss orbital diagrams in our next video, and then this last rule will make more sense to you. Electrons will occupy orbitals of equal energy singularly before pairing up. And we're just going to hold on to that third principle, and I'll illustrate it better for you in the next video. So before we apply these rules, let's kind of take what we learned in the previous video about energy levels and orbitals and add it to the information that we have here. So we discussed in the previous video the first energy level, smallest in size, closest to the nucleus, has only one type of orbital in it, and that orbital is an s orbital. And we give it the number 1 to indicate that it is an s orbital in the first energy level. And remember, it has that spherical shape. There is also only one s orbital present in any energy level beginning with the first. So there would also be an s orbital in the second energy level, bigger in size, an s orbital in the third energy level, even bigger in size, as we drew in the previous video. A fourth energy level, or an s orbital in the fourth energy level, known as the 4s orbital, and so forth and so on. The very first rule of writing electron configurations says that there is a maximum of 2 electrons that can occupy any single individual orbital. So only one s orbital in each energy level, each s orbital, each single one only holding 2 electrons. So the superscript 2 indicating the number of electrons needed to fill. The first energy level is full. It's the smallest. It only has a single s orbital in it holding 2 electrons. So the maximum number of electrons needed to fill the first energy level is 2. And notice I gave a handy little formula that enables you to calculate that, where n is the energy level number, n is 1, we would square that. 1 squared is 1 times 2 gives us the 2 electrons needed to fill the first energy level. Before we even list the orbital types, let's make a prediction using this formula for the second energy level. If n is 2, 2 squared is 4 times 2 is 8. And so this formula is predicting, before we even list the orbital types, that a total of 8 electrons is required to fill the second energy level. Well, what type of orbitals are present in the second energy level? We indicated that in addition to having an s orbital, a single s orbital, the second energy level, because it is bigger in size, also picks up a new type of orbital, the p orbitals. Do you remember that we said that p orbitals always come in a set of 3? And I drew them for you. The 2px, the 2py, and the 2pz orbitals. 3p orbitals always coming in a set of 3, beginning in the second energy level. The third energy level would also have p orbitals, 3px, 3py, and 3pz. Fourth energy level also has p orbitals, so I could continue this drawing, but you see here, wow, there's d orbitals, there's f orbitals. I'm not going to have enough space. So we know that each of these individual orbitals can hold a maximum of 2 electrons. Given that, scientists say, let's just condense here, and let's take those 3 individual p orbitals, each one holding a maximum of 2 electrons, and collapse them together. And so rather than writing this out, we know this is true, we know this is what is there, but it gets a little bulky. We're just going to collapse and say that there are a total of 6 electrons that can occupy the 3 p orbitals present in the second energy level. We just combine it and write 2p6. And that's it. The second energy level is full, and counting the total number of electrons that it can hold, 2 and a 2s, 6 total in the 3 2p orbitals present, gives us 2 plus 6, a total of 8 electrons required to fill the second energy level. Our formula tells us that for the third energy level, we should have a total of 18 electrons needed to fill all of the orbital types of the third energy level according to this formula. 3 squared is 9, and 9 times 2 is 18. Well, what are we looking at in terms of orbitals in the third energy level? We know there is a single s orbital called the 3s. It's in the third energy level. That single orbital holds 2 electrons. We know that there are the p orbitals present in the third energy level, 3 of them. We refer to them as the 3p orbitals, each one holding 2 electrons. 3 times 2 is 6. So total of 6 electrons needed to fill the p orbitals in the third energy level. But you recall that every time we move to a higher energy level, the increased size allows us to add a new type of orbital. And these orbitals are the d orbitals, beginning in the third energy level. And you remember there were 5 of them. 4 had a cloverleaf shape, and 1 had a p orbital shape with a ring around it, for a total of 5 d orbitals present in the third energy level and every energy level above it. So these 5 d orbitals in the third energy level can each hold 2 electrons, for a total of 10 electrons needed to fill all the d orbitals in the third energy level. And that's it. The third energy level can hold no more orbitals of different types. So adding these superscripts together, 2 and 6 is 8 plus 10. We see the 18 electrons needed to fill all of the orbitals present in the third energy level. N equals 4, fourth energy level. Looking at our formula, 4 squared is 16. 16 times 2, 32 electrons needed to fill the orbitals present in the fourth energy level. Well, what are those orbitals? There's the single s orbital, the 4s, which can hold 2 electrons. There are the 3p orbitals found in the fourth energy level. So those 4p orbitals, 3 of them are present, each holding 2 electrons for a total of 6 electrons, filling the 4p. There is also the 4d orbitals. They always come in a set of 5 in any energy level. D orbitals come in a set of 5. So the 4d orbitals could hold a total of 10 electrons because each of those orbitals can hold 2 electrons. So we are in a higher energy level. We know we should expect to see one additional orbital type. So looking at the pattern, the types of orbitals present correlate to the energy level. First energy level has only one type of orbital, an s. Second energy level has 2 types of orbitals, s and p. Third energy level has 3 types of orbitals, s and p and d orbitals. The fourth energy level, 4 types, and this is where we pick up those f orbitals that I briefly mentioned in the previous video. Let me give myself a little bit more space here and call these the 4f orbitals. F orbitals always come in a set of 7. Your book does not show a drawing of them. They're very complex to draw, but they always come in a set of 7. Each orbital holds a maximum of 2 electrons, giving us a total of 14 electrons needed to fill the f orbitals in the fourth energy level. And adding these numbers up, 2 and 6 is 8, and 10 is 18, plus 14 gives us 32 electrons. We could continue filling this table out with n equals 5 and n equals 6, but I think you get the idea. Now, how do we explain, using this information, what's going on with the second rule for writing electron configurations? Electrons will occupy lowest energy orbitals available first and then move to the next highest. Well, what does that mean? Does that mean that first you fill the 1s, then you fill the 2s and the 2p and the 3s and the 3p and the 3d? In other words, is that the order of filling according to energy? And the answer is, you might think so, but not quite. It doesn't turn out that electrons just fill each energy level completely before moving to the next. And why is that? The best way that I can explain it is to give you this analogy, which involves ticket sales at a theater. So suppose you were interested in seeing a musical group, your favorite musical group, at a theater. And the group, of course, is on stage, and the stage represents, for an atom, the nucleus with its positive charge. You're at the theater, you want the best view of the stage where the group is performing. Electrons, when they surround the atom, when they surround the nucleus, want the best view of that nucleus where the positive charge is. So suppose you were at Ticketmaster wanting to purchase a seat, and Ticketmaster said, this is what I have available and open. You could be in a third row with a seat right here, way off to the side. Or you could be in a fourth row, little further back, but front and center. I don't know about you, but I know which ticket I'm purchasing if it were my choice. I'd prefer to be a little further back distance-wise but more centered to the stage, I would purchase this ticket. So center positions for electrons viewing the nucleus, best view from a center position would be in an S-type orbital with that spherical shape. Slightly off-center, meaning not quite as good of a view, right? If you were in the fourth row or fourth energy level, would be a p orbital. P orbital's not quite giving you quite the same view, followed by D, and then of course if you're in the fourth row, fourth energy level, F. So it turns out that electrons will go to a higher energy level to occupy an S orbital rather than filling the orbitals available in a lower energy level if they're more off to the side, as in not quite as good a view of the nucleus because it's either a D or F orbital. So we see that with electrons. It turns out that the order of orbital filling is like this. First you fill the 1s, then you fill the 2s, 2p, 3s, 3p. Notice it looks like we're just 1s, 2s, 2p, 3s, 3p, but right here we do not fill the 3d after we fill the 3p. Instead, we fill the 4s. We choose to, or electrons choose to occupy an orbital in the fourth energy level a little farther away, but it's an s orbital more centered to give it a better view of the nucleus. So after you fill the 3p, then you go to the fourth energy level, start filling a 4s orbital, then you come back and finish the third energy level by filling the d orbitals. Then you'd fill the 4p, and at this particular point you're thinking, oh, this sounds like this is going to be complicated. Good news for you. The periodic table shows the order with which electrons arrange themselves around the nucleus. So again, we're looking at increasing energy of orbitals, and the periodic table tells us what that order is. So let's bring it up here. All you have to do is know how to read it. So, periods correlate to energy levels. And notice this section here with 2 columns in it, that represents s orbitals, which can hold a maximum of 2 electrons. This section here with a total of 1, 2, 3, 4, 5, 6 columns represent p orbitals that require a total of 6 electrons. Then we have a section here with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns across. These would represent d orbitals filling. And finally, we have down here, and I'm going to skip over lanthanum and actinium. They actually belong right up here, and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 columns, that represents the f orbitals that get filled. So, periodic table tells us the order with which orbitals are occupied by electrons. First you fill the 1s, then you fill the 2s. So second period represents the second energy level filling. This section here, s orbitals. You fill the 2s. Then you come over, we're in a p block. In the second energy level, you fill the 2p. Then we're back in an s block. Third energy level, you fill the 3s. Then the 3p, we're in another p block in the third energy level. You fill the 3p. Then the periodic table tells you, wait a minute, you don't fill the 3d, you start the fourth energy level and you're back in an s block. You fill the 4s. For the first time we're in a D block, this has to be the 3D orbitals. It's the first time we've encountered D orbitals, and they are in the third energy level for the first time. So after you fill the 4s, you fill the 3D. So D orbitals always one below whatever the period is showing as highest or outermost energy level. D orbitals are always one below that. 4s, 3D. Now we're back in a P block. This P block belongs to the fourth energy level. So after you fill the 3D, you fill the 4P. Then the 5s, then the 4D, so D block, always one below whatever is the highest energy level holding electrons. 4D, then the 5P. And I know this is a lot to take in the first time, but after you look at the periodic table enough, you just begin to see the flow, and the table is trying to show you what the electron configuration is for each element. So let's just do a couple of quick examples here before we end. Let's take a look at the first and simplest element, hydrogen. It only has one electron. Well, where does that one electron go? Goes in the 1s orbital, the lowest energy orbital available. So I write 1s and the superscript indicating how many electrons are there. Hydrogen has only one electron, so its configuration is 1s1. Let's take a look at an element with more electrons. Oxygen, a very common, very important element. From the work we've done before, and I'm going to use a smaller table here, it's a little harder to keep pulling the big one up, I know the atomic number of oxygen is 8. So if the atomic number is 8 and it is a neutral atom, it also has to have 8 electrons. Where do those 8 electrons go? How do they arrange themselves? Well, the first 2 electrons fill a 1s orbital, and then it's full. It can only hold 2. The next 2 electrons fill the 2s orbital, and then it is full. And the periodic table is showing us that, let me put it back up for a minute. First we fill the 1s with a total of 2 electrons, then the 2s with a total of 2 electrons. We're making our way to oxygen. We have to count 1, 2, 3, 4 columns over, meaning there are 4 electrons in the 2p orbitals for oxygen. So its configuration, 1s2, 2s2, and 2p, 1, 2, 3, 4. So that's what I have written here. 1s2, 2s2, 2p4. It's really important whenever you write an electron configuration to count those superscripts and make sure that you add up to the number of electrons you say the atom has as a neutral atom. So 2 plus 2 is 4, plus 4 is 8. We've accounted for oxygen's 8 electrons. What I'm doing here is writing the complete electron configuration, but notice there's a shortcut because this can get lengthy quickly writing configurations. So we have what we refer to as the noble gas abbreviated configuration. And when you write a noble gas abbreviated configuration for an element, you look at the element and you back up to the noble gas that comes directly before it, which is helium in the case of oxygen, and you just write what comes after helium. So you put helium in brackets and then put 2s2, 2p4. It's not much of an abbreviation for oxygen, but you're going to see that it helps quickly as elements get bigger in size. So the abbreviated configuration for oxygen would be helium. So helium's configuration is represented, right, by this. Let me see if I can find the right color here. Helium's configuration is represented by this 1s2. And then you write what comes after helium's configuration. 2s2, 2p4. Let's do one last example in this video clip. Let's take a look at the element bromine. And if you look at your periodic table, you'll see that bromine has an atomic number of 35, meaning that it has 35 protons in its nucleus and 35 electrons in the neutral atom. So where do those 35 electrons go? What order do they fill the orbitals around the nucleus of a bromine atom? Periodic table is telling us this information. Here is bromine. It's a halogen. So how do the electrons arrange themselves? First, we fill the 1s orbitals with 2 electrons. And you may wonder why helium isn't over here, and there's an answer to that I will explain later. First, we fill the 1s, then we fill the 2s with 2 electrons, 2 p orbitals with 6 electrons, 3s orbitals with 2 electrons, so 3s2, 3p6, 4s2, remember we're in that D block, one below, 3d10, back in the p orbitals of the 4th energy level, 4p, 1, 2, 3, 4, 5. So the periodic table is telling you exactly what the configuration for bromine is, and we can write that here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Before you sign off, you're double checking. Do those superscripts add up to 35? 2, I'm giving you running total. 2, 4, 10, 12, 18, 20, 30, 35. Yes, we have accounted for the 35 electrons found in a neutral bromine atom. But who wants to write all of that? It's faster to write, instead of the complete electron configuration, to write an abbreviated configuration using a noble gas. So the way we would do that is looking at our element bromine, we back up to the noble gas that precedes it, which is argon, put its symbol in brackets, and write what comes after. 4s2, 3d10, 4p5. So that would be the abbreviated noble gas configuration for bromine. Everything up to here represents the configuration of argon. So we put argon in brackets and write what comes after that configuration. 4s2, 3d10, 4p5. So now I've given you 2 different methods for writing electron configurations for elements.